Okay, next we talk about eigenvectors and eigenvalues. And since this is a review, we'll just state it. Um, that consider linear mapping. Okay, we know what linear mapping means. And basically, a linear mapping means it's a function, but it also means that there's a matrix associated with this mapping. So there's some matrix associated with this linear mapping. Such a mapping can be represented with a square n by n matrix. In case for a specific vector x, we suppose that we have this here. That is, if you take a particular x for that matrix, we're given a matrix, if there's an x, which when you multiply a times that x, you just get a scalar multiple of x. So in other words, we know that when we multiply a matrix times x, it will give us a different vector, some other vector, x, some other vector, and but if that other vector happens to be just a multiple of the original, then that's called, that x is called an eigenvector for the matrix A, and the scalar that that it's a scalar multiple of is called the eigenvalue. So this lambda here is called the eigenvalue. Okay, so some interesting things now. If A is symmetric, when we talked about symmetric, it's just not, of course, not every vector, sorry, every matrix is symmetric, but if A is symmetric, then it can be shown that, we might say, well, how many different, okay, suppose we find an X, which has this property that when you multiply it times A, you get just a multiple of x. So that's called, we just said that's an eigenvector for A. But we might ask, well, how many other eigenvectors are there? Not parallel to x, but in some other direction. Maybe there are other ones. So how many are there? So if A is symmetric, it can be shown that there are n eigenvectors and not only that, but they form an orthonormal basis of A. So let's say that again. If A is symmetric, then there are actually n eigenvectors for it. And not only that, but they form an orthonormal basis for A. So they form a basis, an orthonormal basis for A. Okay, and suppose that we take all of those eigenvectors and we make them, we take the normal ones, or the ones that are, that are of unit length, and we line them up vertically so that we can form a matrix. And let's call that matrix U. So U is just these, these are the columns of U. That's just these eigenvectors. Okay, so it turns out that that A then can be written as U times D. Okay, I forgot to say what D is. D is the, we said that there are all these eigenvalues. For each eigenvector, there's an eigenvalue. And we make another matrix, D we call it, which has these eigenvalues down the diagonal. So D is a diagonal matrix whose entries are the corresponding eigenvalues. Okay, so once again, we have this very interesting fact that A can be written as U. Remember, U is just these eigenvectors, basically, put in as the columns. So that's what U is. And then D, we just say what D is. We take the eigenvalues and we put them down the diagonal. And then U inverse, well, if we have U, we can get U inverse maybe. And so this is very interesting. Now we have that if A is symmetric, we can write it like this. Now, who cares about that? Why is that interesting? Well, that's like saying who cares about, so this is called, we're factoring A into a product of three different vectors. I'm sorry, matrices, right? It's factoring because there's multiplication between, this is multiplication, this is multiplication. So why do we care about factoring? Well, let's just take the simplest case. Let's say we take the number 12. So we can factor it, of course we say we can factor it into like 6 times 2, or we can factor it into 3 times 4. So why do we care about that? Well, it certainly helps us, when we're doing algebra and things like that, it's useful. And the same thing with, we have things like this. We have this expression here, and we can factor it like that. Or I don't know, we have this expression here, and we can factor it some other way. Or we have this expression. Well, why do we care about that? Well, it's obviously useful in various ways, in various calculations, and so on. So factoring is quite useful. And now we have this really interesting. This is like taking 12 and factoring it into the product of 2 times 2 times 3. Or anyway, it's factoring a matrix into 3 matrices. So this could be very powerful to be able to do that. It might be very useful when we're kind of doing algebra of matrices. So once again, let's just repeat it one more time. This is only talking about when A is symmetric. But we already reviewed the ideas of eigenvectors and eigenvalues. And we say that when A is symmetric, we can show that there are n eigenvectors that form an orthonormal basis of A. And then we can take those n eigenvectors and we can line them up like this. And we have to make sure that they're their unit size when we do this, unit length. And but we can just scale them to do that. So then we have this interesting vector u, which comes from A. And then it turns out that A can be factored in terms of that u, and D is the eigenvalues along the diagonal, and then u inverse. So this is a very powerful, or possibly powerful, result. And the above equation is called the eigenvalue decomposition. So we're factoring or decomposing A into this. This is called the eigenvalue decomposition. I guess this contains the eigenvalues, the D. And next we're going to see some other kind of decomposition or some other kind of factoring. So being able to factor things is I guess I can say obviously important. And here we're able to factor A, and here we're going to have another way to factor under certain conditions. So these could be very useful. Okay, there's another way to factor matrix A. And this one is actually more general in the sense that it doesn't require A to be symmetric or even square. Remember, when we were talking about this type, we insisted that A has to be symmetric in order to do this. But this one says given any matrix A. So given any matrix A, we're going to be able to factor it into a couple different matrices. So what are these matrices? So we have something called D. It's a little different than the other D, but sort of basically the same thing. And we have U, which is sort of the same thing. And we have V. Now remember, before we had U, D, and U inverse. So it doesn't look exactly the same. So the first thing they note is that actually, D is not going to be really the same. It's not going to be a diagonal matrix or truly a diagonal matrix. Because if you look at the size of D, it's m by n. So what would it mean to be a diagonal matrix, right? You can't really have a diagonal matrix unless you have a square matrix. So it just means that the elements dii, so sort of down the diagonal, except the bottom part, it doesn't necessarily reach the bottom part. But anyway, the items that sort of dii that are along the sort of the diagonal, those um, are the only non-zero elements in the matrix D. Okay, but anyway, this is different, a little bit different than before. So remember that before U was a bunch of, well, it was the eigenvectors, but those were, we said, an orthonormal set, so they were all perpendicular. So now in the singular value one, it's also going to be an orthonormal set of vectors, but it's not going to be the eigenvalues, I'm sorry, the eigenvectors of the original matrix A. So instead, they're the eigenvectors of A times A star. So what is A star? A star is basically just the transpose. Now, they get a little more particular here, and they say the conjugate transpose. So if you remember from, when you talk about the square root of -1 in high school or whatever math, you have two parts. So when we're talking about imaginary numbers or complex numbers, they have two parts. We have the two, like something like 2i plus 3. So this is called the imaginary part, and this is called the real part. Actually, let me write it as 3 plus 2i, so just put the 3 first. So the conjugate of this, if you remember, is just 3 minus 2i. So 3 minus 2i is called the complex conjugate of 3 plus 2i. So that's all we mean by the complex conjugate. But also remember that if you just have the number 3, in other words, if you don't have an imaginary number, just a regular real number 3, and you ask what's the complex conjugate of that, it's the same. The complex conjugate is 3. The complex conjugate of 3 is 3. So here they're saying A star is the conjugate transpose. So it just means that if there are any complex numbers in A, then you have to take the conjugate of those. But generally, we won't have any complex numbers in our matrices, so we don't have to worry about that. But if you did, you just have to take their conjugate first, and then take the transpose. But if all the numbers are just real numbers, then when you take the conjugate, you just get the same one. So then you just take the transpose of that. So that's what this is. So we can just think of it as the transpose. Now, if you remember, though, that A times its transpose, we mentioned this earlier, that is a symmetric matrix. So that's probably not that hard to show that, actually, because what do we mean by a symmetric matrix? Well, we know what we mean sort of in terms of, the mirror image, but we have another definition also, and that is that the matrix is equal to its transpose. So if I want to show that this is symmetric, I just have to use that idea, so it's probably not that hard. But anyway, we won't worry about it. We'll just accept that this is going to be symmetric. Okay, so what are we talking about again? So U consists of a set of orthonormal vectors, but where do these come from? So we know about orthonormal vectors from a symmetric matrix, but we're not saying. But we don't know that U is symmetric. In fact, generally speaking, U won't be symmetric. I'm sorry, not U, but A won't be. A is not symmetric, and so we can't do the same thing that we did earlier. But A times its transpose will be symmetric, so we can do the same thing as before and get the eigenvectors and form the matrix with those eigenvectors, and call that U. And that's what this U is. So it's not the eigenvectors of A, it's the eigenvectors of A transpose, or A star. And that we can do. And then D is the eigenvalues for that. And then so U is the eigenvectors of A star. That's here. And then this V is the eigenvectors of A star A. So it's not the same order, right? This is A star, this is A star A. So they probably have different eigenvectors. And so that's what V is. V is the eigenvector of A star A, and then we take the transpose. Okay, so that's a little bit, that's pretty complicated. But the point is, the main point is that we have a way to factor A. And before, it was a way only to factor A when it's symmetric, but this applies for every A. So that's kind of more powerful, more useful, or at least it could be more useful than the eigenvector or eigenvalue decomposition. So, so that's the point, that we can factor A, even if it's not symmetric, and this will be the factorization. And that can be pretty useful when we're playing around kind of with the algebra of matrices.